this session, who is Michele BUCELLI, again from the heart group. And he's going to talk about staggered scheme for the numerical simulation of the heart, coupling 3D electrophysiology, mechanics, and fluid dynamics.
Okay.
Michele,
You confirm you see the slide and hear me fine?
Yeah, everything is fine. You
okay.
can go.
Thank you. So good afternoon, everyone. As Ivan was saying, my presentation would be about our proposed scheme that aims at a coupled simulation of three-dimensional models for cardiac electrophysiology, solid mechanics, and fluid dynamics. The figures here, the animations here on the right, show the kind of computational model that we aim at. So a model in which electrophysiology triggers the contraction of the myocardium, which interacts with the blood within the heart and causes its ejection through the aorta. So we refer to this kind of approach as a fully integrated model in the sense that, as I was saying, it involves a three-dimensional description of all the physical phenomena that are involved. The idea behind this kind of model is that we are able to incorporate explicitly all sorts of feedback between the physical phenomena that concur to the function of the heart. We consider a healthy heart, so a human heart in physiological conditions, and we aim at a simulation that spans multiple heartbeats. So in particular, we do not want to limit ourselves to any particular phase of the heartbeat, say systole or diastole, but want to be able to represent all different phases. So the first part of my presentation will describe the model. This here is a general perspective. We can see the model as composed of four major building blocks. We will refer to them as core models. They are electrophysiology, activation, solid mechanics, so the displacement of the muscle, and fluid dynamics. They are defined either in this domain on the left, omega S, which represents the myocardium, or in the domain omega F, which instead represents the volume occupied by the blood within the heart. The different models, the different core models interact, of course, and they do so either within omega S or through the interface between omega S and omega F. This general picture shows that the model we aim at is a multi-physics model, and it also involves multiple scales, as we will see in a moment, so that the numerical scheme, which we will have to put in place for its solution, will have to be tailored around this. In a bit more detail, let's start from electrophysiology. We rely on the monodomain equation coupled with the 10^-pound Pamphilov ionic model, which is suitable for ventricular simulations. The main output of this block is the calcium concentration, which is hidden inside this vector W of ionic variables, the intracellular calcium concentrations, which is very important for muscular contraction. I would like to point out that already at this stage, we can see these terms here, J and F, appearing in the monodomain equations, and they account for the feedback of solid mechanics on electrophysiology. So they represent the effect of the solid deformation onto the electrical activation of the muscle. The next step is what we call the activation model, which is a model that takes in input, again, the muscle deformation, D, and the ionic variables, and provides as an output this vector of state variables that represent at every point in the solid domain, omega S, the state of contraction of the muscle. To this end, we rely on a highly detailed model that was proposed by Francesco Regazzoni and co-workers. I say highly detailed in the sense that it involves an accurate description of phenomena that happen at the subcellular scale. Due to its complexity, the model is surrogated by means of an artificial neural network, which reduces its computational cost. This again was proposed and implemented by Francesco Regazzoni and co-workers. Now, the activation variables S are fed to the solid mechanics model. This is represented by means of the usual elastodynamics equation. Here, the stress tensor is additively decomposed, as is often done in the literature, in two terms, the passive term and the active term. The passive term essentially accounts for the elastic properties of the material, and we treat it in the hyperelastic framework. We make use of the Guccione model for ventricular tissue, and we use instead the Neo-Hook model for other tissues, mostly valve rings in our ventricular simulation. In both cases, we treat the material as nearly incompressible, so we penalize local changes in volumes. Concerning the active contribution, instead we have some active tension depending on activation state, which is directed along the fibers of the cardiac muscle. The final piece of our model is fluid dynamics. Now we operate in the ALE framework, so we have fluid dynamics in a moving domain, and the first three equations in our fluid dynamics block, let's say, are concerned with the extension of the solid displacement from the fluid structure interface to the whole fluid domain. We do so by means of an arbitrary linear operator. We typically rely on linear elastic lifting for this purpose, since we have found linear elasticity to be robust enough for our simulations. Then, concerning the fluid dynamics model itself, we rely on Navier-Stokes equation for a Newtonian incompressible fluid, so I surely do not need to go into detail about them. And the last two equations here represent the coupling of the fluid and the solid through their interface. So they are continuity of the velocity and continuity of stresses. The whole set of equations that you can see on this slide constitute the model we aim at solving. Now, of course, it is quite a complex model. There are many different equations, many different variables, and most importantly, there are many different coupling terms and sources of feedback between the different equations. So the numerical scheme that we will describe in a moment will have to deal somehow with all these challenges. Let me start by describing the time discretization scheme, which also gives the broad picture of how we deal with the coupling of the different equations. First of all, we use a finite difference discretization for approximating time derivatives appearing in equations, and we rely on a staggered in time coupling scheme. What do I mean by that? At the beginning of every time step, we perform a few small time advancement steps for the electrophysiology model. Then we take the last computed vector of ionic variables and send it to the activation model, which is solved for one single large time step. And the the activation state S is fed finally to the mechanics model. And fluid dynamics and mechanics equations are solved in a tightly coupled way, strongly coupled way, again with a larger time step. This kind of staggered scheme allows us to use a finer time discretization for electrophysiology, which is required for accuracy purposes, since the time scales of the electrophysiology related phenomena are much smaller than the ones related to other phenomena. I'd like to point out that some of the coupling terms are treated in an explicit way, but our experiments didn't find any issues concerning stability due to this explicit treatment. On the other hand, of course, this kind of approach facilitates both implementation and reduces computational cost with respect to a hypothetical fully implicit coupling scheme. Concerning space discretization, we rely on the finite element method on hexahedral grids, and we use bilinear elements for all equations involved. Again, electrophysiology has higher accuracy requirements. The spatial scales that characterize electrophysiology are smaller than the ones of, say, solid mechanics. So we use two nested grids, one very fine for electrophysiology and a coarser one for solid mechanics and activation. And whenever some variable has to be communicated between the two grids, we perform either an interpolation or a projection step. On the other hand, fluid and solid meshes are discretized in a conforming way at their common interface. Now, I would like to spend a few more words on our approach to the solution of the FSI problem, of the fluid structure interaction problem. We treat geometric coupling in an explicit way. That is, at the beginning of every FSI step, we update the fluid domain using only once and using the last available solid displacement at endocardium. On the other hand, the other two coupling conditions, which are the continuity of velocity and stresses, are treated in an implicit way. There is strong coupling of those conditions. The reason is that doing otherwise causes issues due to time instability. So to achieve this implicit coupling, we use the so-called monolithic approach. That is, we discretize both the fluid and the mechanics equations into a single nonlinear algebraic system. Such system is then linearized with Newton's method and solved. The linear system arising from the linearization is solved with the precondition GMRES. We have found that this monolithic approach is more robust and more efficient with respect to other partitioned approaches, let's say, that are based on subiterating between fluid and solid. Of course, the efficiency largely depends on the availability of a good preconditioner for the linear system. To that end, we use the block triangular preconditioner that you see here on the bottom right, which falls back onto the simple preconditioner for approximating the fluid matrix and on algebraic multigrid for approximating the solid matrix. So let's see some results of simulation in this context. I will briefly describe the simulation setup. So we start by obtaining our initial configuration for the structure that is consistent with the end diastolic phase of the heartbeat, which is where we want our simulation to start. And we do so by inflating the ventricle to end diastolic pressure. For epicardial boundary conditions, we use generalized Robin conditions to model the presence and the effect of pericardium, whereas we keep fixed inlet and outlet sections. Concerning the fluid instead, as I said, we want to model different heartbeat phases, so we have somehow to account for the opening and closing of valves, and we do so in quite a simplified way by switching boundary conditions on inlet and outlet sections throughout the computer simulation. Essentially, when a valve is closed, we model it with a no-slip condition, so we allow no flow through the section. Conversely, when aortic valve is open, we use a resistance condition, and when mitral valve is open, we use a pressure condition with a time-dependent pressure that incorporates somehow the atrial contraction. One important point here is that opening and closing of valves in this simulation does not happen at prescribed times, but happens according to simulation results. So valves open when the pressure jump across them becomes positive, and close when backflow occurs through the respective section. To give you an example, the aortic valve starts closed, isovolumic contraction starts, and when ventricular pressure becomes greater than PAV, the valve opens. Vice versa, when flow becomes negative through gamma AV, the valve closes. This slide here reports the results of the simulation. So we can see, starting from the left, the electrophysiology, the activation of the muscle, of the ventricular muscle, which triggers the contraction of the myocardium, and the interaction between the myocardium and the blood causes the blood to be ejected through the aorta. Then aortic valve closes, the ventricle relaxes, and at some point mitral valve opens, the ventricle can fill again, and a new heartbeat starts. I've also reported here pressure volume loop and volume and pressure plots, and from these plots we can see how some relevant biomarkers are quite correctly captured by the model, especially concerning the peak systolic pressure or stroke volume, or even inlet and outlet flow rates. So where do we go from here? What are the main points that still need to be tackled in our model? We have worked on establishing mathematical and numerical framework for the coupling of all the different models that I presented. But what we lack is what we call geometric integration. So the possibility to incorporate in our model not only multiple physical phenomena, but also all the different chambers of the heart. One particular consequence of this is that, for instance, in our left ventricular simulation, it is hard to capture correctly the shortening of the ventricle or the displacement of the atrioventricular plane. These kind of issues are to be addressed, and we aim to do so by moving towards a geometrically integrated description of the heart. So from the left ventricle to the left heart, so incorporating the left atrium and maybe ascending aorta, to a fully coupled, fully integrated simulation of the whole heart with all 4 chambers. To this end, we will have to give a more detailed model for valves, and we aim to do so in the immersed framework using the resistive immersed implicit surface model. Finally, the last piece will be the incorporation in our model of the feedback between the heart and what is outside the heart. So the incorporation of a coupling between our cardiac model and a closed loop model, probably 0-dimensional, for systemic circulation. So that's it for my presentation. Thank you for listening. And of course, I am open for questions if you have any.
Thank you very much, Michele. And we have time for some questions from the audience. Okay. You can either raise your hand or just switch on your camera. Okay, well, in the meantime, I would have actually a question about the computational effort of the whole, the fully, let's say, coupled system, in the sense that my question is about what part, let's say, of the system, what physics is taking, let's say, the most part in computational cost, or if there is any kind of balance between the different components.
Well, thank you for the question. I'd say that there is quite a balanced contribution to the overall cost between electrophysiology and FSI. On the one hand, electrophysiology is not a very difficult problem to solve, especially if you use the monodomain equation. But as I said, we use finer discretization in time and in space for its solution. So its simplicity is balanced by the higher resolution. On the other hand, FSI is more complicated, is nonlinear. There are all sorts of issues related to it. So it has a high cost, but we solve it on a coarser grid in time and in space. So there is kind of a 50-50 split between the two models. Activation in this context has a cost that is almost negligible if compared to the other two.
Okay, thank you.
May I have a question?
Yes, please.
When you interpolate data from electrophysiological mesh to mechanical mesh and back, you introduce errors and you may lose masses. How you cope with this?
Well, the interpolation from the coarse mesh onto the fine mesh, since the two meshes are nested, is exact, and there is no error there. I agree that we do lose something when projecting the result of electrophysiology onto activation, and the quantity essentially that we need to project is the calcium concentration from the fine mesh onto the coarser mesh. However, the projection actually has a regularizing effect, so it smooths out the calcium concentration, and so actually this is even helpful towards the simulation. Actually, we do this projection and we include a small smoothing to accentuate this effect.
Okay, thank you.
Okay. By that, we can say that this session is concluded. I want to thank once again all the speakers, and we can move to the the main room for the final plenary session of this conference. Thank you very much, everybody.
Thank you.